Before stars, before time, before anything could be named, there was only a silent pressure. A state without space, without direction, without meaning. Then, in a moment smaller than a thought, existence unfolded. Not as an explosion inside empty space, but as the creation of space itself. Time began to flow where it had never flowed before. Energy surged outward, stretching the newborn fabric of the universe faster than light could ever move. In that first fraction of a second, the foundations of reality were written. Gravity found its strength. Light separated from matter. The forces that would shape every star, every galaxy, every living world took form within a storm of unimaginable heat. The cosmos expanded violently, yet with a delicate precision that allowed structure to emerge from chaos. Space widened. Matter cooled. Patterns formed, the earliest hints of galaxies, hidden inside a swirling ocean of plasma. Everything that would ever exist was already beginning to take shape, carried inside that first shimmering brightness. And if the universe could speak in that moment, its voice would say, "I did not appear inside space. Space appeared inside me." From my first moment, everything that would ever exist was already beginning to remember its shape. In the first 10 superscript 3 seconds of existence, the universe was a place beyond anything our physics can fully describe. Temperatures were so extreme, densities so absolute, that the familiar laws of nature had not yet separated into the forces we know today. Gravity was not distinct. Electromagnetism had no identity. The strong and weak nuclear interactions were merged into a single, undefined state. Reality itself behaved like a storm of pure mathematics, a chaotic field in which space and time flickered in and out of form. This epoch is called the Planck era, the moment when the universe was smaller than an atom yet contained all the energy that would one day become galaxies, stars, planets, and life. Space was not smooth. Instead, it may have resembled a kind of quantum foam, a restless landscape where tiny fluctuations created temporary bubbles of space-time, rising and collapsing in an instant. Some theories even suggest that each bubble could have become an entirely separate universe, branching away from our own before time had a chance to take its first breath. We cannot observe this era directly. No light, no particle, no signal from that moment can reach us. But the mathematics left behind, the structure of quantum theory and gravity, allows us to trace the edges of that beginning. Through equations rather than telescopes, we glimpse a reality where everything we know was waiting to unfold, bound inside a chaos that has no true parallel in the modern cosmos. After the Planck era, the newborn universe cooled just enough for its perfect symmetry to begin breaking. In a fraction of a second, the most fundamental transformation in all of physics took place. Gravity separated first, stepping out of the unified state and becoming its own distinct interaction. As temperatures continued to fall, the strong nuclear force separated next, followed by the electroweak force, which later divided into the electromagnetic and weak interactions. With every division, the rules of reality became more defined. The laws that govern atoms, stars, and galaxies were being written in the fabric of spacetime itself. This moment marks the true foundation of physics, the architecture upon which the entire universe would evolve. Forces were no longer blended into a single, indistinguishable entity. They gained identity, strength, and purpose. The symmetry, once perfect, fractured into a structured set of interactions that would guide how matter clumps, how light moves, and how energy transforms. It was the universe choosing the parameters of its own existence. At the same time, an explosive expansion began, cosmic inflation. In less than a heartbeat, space stretched faster than light, enlarging the universe by unimaginable factors. Tiny quantum ripples, once smaller than subatomic particles, were pulled across vast cosmic distances, becoming the seeds of all future structure. These microscopic fluctuations would evolve into galaxies, clusters, and the grand cosmic web. Inflation smoothed the universe, flattened it, and set the initial conditions for everything that would follow. The calmness of the sky today hides the violence of this birth. The moment when forces emerged and space itself exploded outward, carrying the blueprint of the cosmos with it. After the violent burst of inflation ended, the universe did not settle into calm. Instead, space reheated dramatically, filling itself with an ocean of raw energy dense enough to create matter directly from the vacuum. Out of this energetic storm emerged the first building blocks of reality: quarks, leptons, and photons. The early cosmos became a seething plasma where particles and antiparticles flashed into existence and vanished again in constant annihilation. Quarks moved freely, unbound, as if swimming through a hot cosmic fluid. Electrons and neutrinos drifted through the chaos while photons scattered endlessly, unable to travel in a straight line through such density. As the universe continued to expand, temperatures slowly dropped, allowing quarks to combine into trios, forming the first protons and neutrons. These were the seeds of atomic nuclei, the foundation of every chemical element that would ever exist. But the early particle era was still a battleground. For every particle, an antiparticle appeared, and the two would collide, releasing pure energy. Perfect symmetry should have erased everything, matter and antimatter canceling each other out in a final flash. Yet the universe contained a tiny imperfection, a subtle imbalance written into its laws. For every billion annihilations, one extra particle of matter survived. This small excess, one left over in a billion, is the reason anything exists today. All stars, planets, oceans, mountains, and every living being trace their origin to that microscopic asymmetry. In those first fleeting moments, the universe chose matter over nothingness. And from that choice, our entire world was born. As the fireball of the early universe continued to expand, its temperature fell from the unimaginable heat of the particle era into a range where the first nuclei could finally take shape. Only a few seconds had passed since the beginning of time, yet the cosmos was already preparing its first chemistry. Protons and neutrons, now stable enough to exist in meaningful quantities, began to merge through nuclear fusion. Out of this brief window of extreme heat and density, the earliest atomic nuclei were born. Hydrogen in overwhelming abundance, helium in significant amounts, and a trace of lithium, the first generation of elements in the universe. For a moment, reactions occurred in every direction, forming and unforming nuclei as fast as the expanding space allowed. But the universe was cooling rapidly. After roughly 3 minutes, the temperature dropped below the threshold required for further fusion, and the nuclear reactions froze in place. The proportions established in those first minutes, about 75% hydrogen and 25% helium, with only a whisper of heavier nuclei, became the permanent chemical fingerprint of the cosmos. Billions of years later, precise measurements of ancient gas clouds and the radiation of the cosmic microwave background perfectly matched these early predictions, confirming that this brief era of nucleosynthesis wrote the first chapter of the universe's elemental story. Our understanding of the universe's earliest moments is not built on speculation. It is grounded in precise measurements and experiments that echo the physics of the first seconds after the Big Bang. The most important evidence comes from the cosmic microwave background, the faint afterglow released when the universe became transparent roughly 380,000 years after its birth. Missions such as WMAP and the Planck satellite have mapped this radiation across the entire sky with extraordinary accuracy, revealing a temperature of 2.725 Kelvin and tiny fluctuations that reflect the distribution of matter and energy in the infant cosmos. These patterns confirm the predictions of nucleosynthesis, inflation, and the formation of the first elements with remarkable precision. But the evidence does not end in space. On Earth, particle accelerators like the Large Hadron Collider and the relativistic Heavy Ion Collider recreate miniature versions of the conditions that existed microseconds after the beginning of time. In these experiments, quarks and gluons behave exactly as the models of the early universe predict, forming a hot quark-gluon plasma indistinguishable from the state that filled the cosmos before nuclei condensed. Together, the sky's oldest light and the laboratory's highest energies form a coherent picture. The physics of the first seconds is not only mathematically consistent, but experimentally verified across the largest and smallest scales of existence. In the end, everything we know, every star, every atom, every breath of life, traces its origin to the first few seconds after the universe began. In that brief, unimaginable moment, the fundamental forces separated, the first particles emerged, and the initial blueprint of reality was written into the fabric of spacetime. The proportions of hydrogen and helium, the seeds of galaxies, the distribution of matter, all were set before a single star was born. As the cosmos expanded and cooled, it simply unfolded the instructions encoded in those opening instants. The story of the universe is vast, but its foundation is remarkably small. A handful of seconds that determined everything that would follow. The first seconds were not just the beginning, they were the foundation of everything that will ever exist.